Now there is a new thing, that is radioactive branching. Radioactive branching. Okay. Suppose you have parent nuclei X. This parent nuclei can decay to, in most cases, in most cases, for each parent nuclei, there is corresponding a single daughter nuclei. I mean, X will decay to Y. So it is, fixed that uranium will go to some polonium and so on. Okay. So what I'm saying, for each nuclei, the decay is fixed. Like say X will decay to Y and that Y will be fixed. But some radioactive parent nuclei can decay to Y, or it can decay to Z also. Suppose this X nuclei is decaying to daughter nuclei Y. You can take, cap symbol also here. Suppose this X parent nuclei is decaying to Y daughter nuclei by emitting alpha particle with decay constant lambda alpha. At the same time, this parent nuclei decaying to Z by emitting beta particle with decay constant lambda beta. Okay, so this is a rare case, because as for each parent nuclei, this daughter nuclei is fixed. That X will decay to Y. The chain is single chain. But few parent nuclei will not follow like this. They can decay to Y. At the same time, they can decay to Z by different radioactive particles. Okay, with decay constant lambda alpha, lambda beta.
Sir?
Yes.
Sir, it Y decay होगा ही होगा Y में always.
No, what I'm saying, suppose, what I'm trying to say, please listen to me. What I'm saying, suppose you have a X parent nuclei. Yesterday we discussed, right? It's decaying to Y. Some there you have X, like suppose you have a uranium. That is decaying to some that is decaying alpha particle, and it's going to suppose to other radioactive nuclei or some daughter nuclei. And the chain is single chain. X is decaying to Y, right? And you know that cause of radioactivity, right? So what I'm trying to say, that most of the radioactive nuclei will follow that single chain. X will decay to Y. So for each X, there is a identical Y. If I give that example, then it will be clear to you. Okay, let me give that example, then it will be clear to you. For example, suppose you have a uranium 92 238 is decaying to thorium 90 and 234, and you have an alpha particle. You can see that whenever you have a uranium nuclei, it will decay to thorium nuclei. So you have an X here and corresponding Y that is fixed. If this is your X radioactive nuclei, it will only follow a single chain and it will go to daughter nuclei. But there is some certain radioactive nuclei, they will not follow single chain. Rather, they can decay, like they can decay by alpha particle, and they can goes to Y daughter nuclei, and they can decay beta particle, and they can go to Z daughter nuclei, and it's happening at the same time. Now,
one particle at a time undergoes alpha decay and beta decay.
yes,
Okay.
the process is happening at the same time, and it can achieve stability by emitting alpha decay, or it can achieve stability by emitting beta decay, or gamma itself, gamma also. But this, please keep in mind, this this process is very rare. There is very less radioactive nuclei, they will follow this kind of scenario. Otherwise, most of the radioactive nuclei will have single chain.
सर सॉरी मैं कंफर्म करना चाहती हूँ कि मतलब x एट द सेम टाइम अल्फा डीके करके
Suppose,
y
हाँ
में और एट
हाँ
द
सपोज,
सेम उसी टाइम बीटा डीके करेगा.
हाँ देखो पॉसिबिलिटी ये है कि सपोज मान लो आपके पास x जो है बिगर साइज है,
यस सर.
दे कैन अचीव स्टेबिलिटी बाय इमिटिंग अल्फा पार्टिकल. और सपोज मान लो x के पास जो n/j रेशियो है, सपोज मान लो x के पास जो n/j रेशियो है स्टेबल होने के लिए वो उतना है नहीं, तो इट कैन अचीव बिकॉज ऑफ large size, it can decay alpha particle and it can achieve that stability. And it has that n/j ratio is not the required value, then it will emit beta particle and can achieve that stability. Is this clear what I'm saying? You have to clear more.
Sir, sorry, I am asking again, but still I'm confused. Is there is an and or meter at a time alpha and beta will be omitted, or is it possible that at some times beta will emit or at some times alpha will emit?
Then what is the condition? What is the condition behind that? That this will achieve stability by emitting alpha particle, and what is the condition that it will emit beta particle? Is there any, will there be any control parameter here? Will there be any control parameter? The cause of instability because of large size and n/j ratio. I mean, you try. I'm not. You are not listening actually my words. What I'm trying to say. मैं कह रहा हूं कि ये जो प्रोसेस है बहुत रेयर है. सारे रेडियोएक्टिव न्यूक्लिया एक्चुअली सिंगल चेन को फॉलो करती है, बट कुछ रेडियोएक्टिव न्यूक्लिया में ये कैरेक्टरिस्टिक है कि एट द सेम टाइम दे कैन इमिट अल्फा पार्टिकल. अब ये समझो, एक पार्टिकल को लेकर क्यों समझ रहे हो आप? इसके पास आपका सपोज मान लो बहुत लार्ज नंबर ऑफ वैल्यूज है, 10⁻n है. एक्स न्यूक्लिया आपके पास एट द सेम टाइम 10⁻n न्यूक्लिया है. इनमें से कुछ अल्फा पार्टिकल अल्फा इमिट करेंगे एंड विल कन्वर्ट टू वाई, और इनमें से कुछ बीटा इमिट करेंगे एंड दे विल कन्वर्ट टू जेड. आपके पास एक अल्फा पार्टिकल थोड़ी ना, एक्स न्यूक्लिया थोड़ी ना है. यू हैव लार्ज नंबर ऑफ पैरेंट न्यूक्लिया इन a sample.
Yes sir.
Is it clear now?
Yes sir.
Yes, sir.
So cause you understood now. What is the cause that they can simultaneously emit that particle? Because of instability, maybe the region of bigger size or n/j ratio is not suitable value. So now can you tell me what will be the total decay constant here? Total decay constant. Can you tell me what will be the total decay constant of X nuclei? You know that decay constant is nothing but lambda, right? So total decay constant of X will be how much?
Lambda alpha plus lambda beta.
Exactly. So lambda alpha plus lambda beta. At the same time, if it is emitting gamma particle, it is converting to some other particle. Suppose I'm giving some number name. Don't take. I'm taking some suppose what I'm trying to say. At the same time, this X nuclei is also achieving stability by emitting gamma particle, and suppose that decay constant is lambda gamma. It may happen that simultaneously it is emitting alpha particle, beta particle, gamma particle. Then total decay constant of X will be, you have to add gamma also.
Plus lambda gamma.
So, but for the time being, I'm only considering this. Okay, but it may possible. And can you tell me, can I write that lambda alpha? I can write like 0.693 divided by
T half.
half life T half for alpha decay. T half for, I mean, lambda alpha means what? 0.693 divided by half lifetime of the sample in alpha decay. And lambda beta I can write 0.693 divided by half lifetime of the sample in beta decay. And this is the total decay constant of this sample. Is this clear what I'm saying? हाँ ना बोल दिया करो.
Yes, sir.
Yes, sir. Yes, sir.
Well, now another concept is known as branching ratio. What is branching ratio actually? Branching ratio. So I mean, your parent nuclei is decaying in different branch, right? In alpha branch, beta branch, gamma branch, and so on. Now, if I define that branching ratio for alpha decay, then how will define the rate of change of parent nuclei due to alpha decay and divide by a rate of change of parent nuclei or total rate of change of parent nuclei. But remember, I have assumed what I have assumed. We have a parent nucleus, it is decaying to Y and Z by alpha and beta with lambda beta and lambda alpha. So branching ratio for alpha decay, rate of decay in alpha divided by total decay. Now, can you tell me this value? dN by dt in alpha decay, that will be how much? That will be nothing but n into lambda alpha, right? We know this thing, and this will be minus n into lambda x or total decay constant. N will be cancelled, minus will be cancelled, and I'll get lambda alpha divided by total decay constant. So branching ratio for alpha decay, that will be decay constant in alpha decay divided by total decay constant, right? Total decay constant of parent nuclei x. In terms of half lifetime, it will be how much? कितना हो जाएगी branching ratio? So you know there is a reciprocal relationship between lambda and a half life, right? We have derived this thing, right?
Yes, sir.
What I'll do, just I'll substitute that values. If you substitute this value, basically you will get a half life or total half life of parent nuclei divided by half life in alpha decay. And also we have noticed that lambda is nothing but 1 by mean lifetime, right? So in terms of mean lifetime, also you can write that it will be mean lifetime in alpha decay, sorry, total mean lifetime of parent nuclei divided by mean life in alpha decay. Check karo jara, if you have any doubt, tell me. So branching ratio for alpha decay will be rate of decay in alpha divided by total decay rate, and dN by dt, you know, you have a n, that is n naught e the power minus lambda t, and you know that dN by dt is nothing but minus lambda n. So you have a alpha decay, for that you will have minus lambda alpha n, and total decay, that will be minus n decay constant, and you have a reciprocal relation of lambda with t half as well as mean life. Just we have substituted that values.
Sir,
Haji?
sir, T half for X. Total T half will be T half for alpha plus T half of beta and plus T half of gamma if there will be gamma admission. So in this case,
you tell me what will happen. T half, total T half means what?
total T half जो X के लिए है, वो T half of alpha plus T half
no,
of.
not necessary. I mean, you don't know in which branch there is a highest decay rate.
Okay.
हमको पता नहीं ना आपका अल्फा में ज्यादा डीके हो रहा है या बीटा में ज्यादा डीके हो रहा है, दैट वी डोंट नो। बट टी हाफ का मतलब, टी हाफ ऑफ एक्स का मतलब क्या है, यहाँ पे n नॉट नंबर ऑफ पेरेंट न्यूक्लियाई, the time taken at which, time required at which that n naught becomes n naught by 2, that will be the half life of this thing. And what will be the meaning of t half in alpha?
Time in which and not
हाँ, अगर सपोज मान लो आपका
alpha
अल्फा इमिट होता है तो कितना टाइम लगता है हाफ होने के लिए, दैट विल बी योर टी हाफ इन अल्फा।
मतलब सर जिसका कंट्रीब्यूशन ज्यादा होता है वही हम लेते हैं क्या T1/2 x में?
From here you can understand now what is the meaning of branching ratio, tell me. You see, branching ratio किसके ऊपर डिपेंड है, टोटल डीके कांस्टेंट बाय लैम्डा अल्फा, राइट? तो
Yes.
डीके कांस्टेंट का मतलब क्या है, डीके कांस्टेंट किससे रिलेटेड है, रिलेट है
Yes,
डीके रेट से, dn by dt that is proportional to lambda, right?
Yes, sir.
तो अगर सपोज मान लो अल्फा में ज्यादा हो रही है तो लैम्डा अल्फा भी ज्यादा हो गया, आई डोंट नो, ठीक है ना? तो उस केस में ब्रांचिंग रेशियो किसका, आपका अल्फा का ज्यादा हो जाएगी। बट इफ यू हैव lambda beta is greater, then this ratio will be large. That's why this ratio is having significance or importance. But अब ये जरा बताओ कि जो टोटल डीके, सॉरी टोटल जो ब्रांचिंग रेशियो होगी, इफ यू सम, तो क्या होनी चाहिए? Just we have derived, okay, I'll finish that. But tell me, you have you got this branching ratio in alpha decay. Now tell me what will happen to branching ratio in beta decay. Same rule will be applicable. Rate of decay in beta divided by rate of decay or total rate of decay, right? And that will again be like lambda beta by lambda x, and that will be again what I can write, that t half or total half life by t half in alpha decay. That can further be written as mean life or total mean life by mean life in alpha decay. So you can see branching ratio alpha का कितना थी, lambda alpha by lambda x, and beta का lambda beta by lambda
सर ये टी हाफ बीटा नहीं आएगा?
हाँ, yes, very good, very good, yes, thank you, this will be beta. Okay, ठीक है? अब टोटल आपने ब्रांचिंग कितना था आपके पास, you have 2 branching, right, alpha and beta. So total branching ratio कितना हो जाएगी, total branching ratio? That will be branching ratio in alpha, branching ratio in beta, because we have assumed only there's a 2 decay channel, one is alpha, another is beta. That's why you have taken alpha and beta. If you have gamma, then you have to consider that gamma also. But if you sum or total branching ratio will be how much? देखो, you have a, like lambda alpha plus lambda beta by lambda x, and we have seen that lambda alpha and lambda beta is nothing but lambda x, right? So lambda x by lambda x, that will be unity. So total branching ratio will be unity. But ठीक है ना? Tell me if you have any doubt. No? Okay, then let us solve the problems. Please write the problem. A radioactive sample can simultaneously a radioactive sample can simultaneously decay alpha and beta particles. A radioactive sample can simultaneously decay alpha and beta particle with mean life of on 620 and 405 years 405 years respectively. A radioactive sample can simultaneously decay alpha and beta particle with mean life of on 620 and 405 years respectively. Full stop. Find the time during which 3/4 of the sample will be decayed. So a radioactive sample that can simultaneously decay alpha and beta particle with mean life of 1620 and 405 years. So find the time during which 3/4 of the sample will be decayed. ठीक है ना? Well, so as you know, first of all, you have to calculate the total decay constant, and that will be lambda alpha plus lambda beta, because decaying alpha and beta particles. And you know that decay constant is related to mean life, right? So that I can write, excuse me. So there is a reciprocal relation. So in place of lambda alpha, what I can write, the mean life of alpha particle, and in place of lambda beta, I can write mean life in beta decay. Why? Because you have derived that mean life is nothing but 1 by lambda, right? You have derived that, and that is given. So lambda will be how much? So you have a 1 by 1620 and you have a 1 by 405. ठीक है ना? Year inverse. Okay. So if you calculate this value, okay, you will basically get 1 by 324. Year inverse. So 3/4 of the sample will be decayed means what? You have a, suppose initially you have a n naught number of, suppose you have a n naught number of nuclei. So number of undecayed, if there is a 3/4 number, 3/4 of the sample decayed means 3n naught by 4 will be decayed. 3n naught by 4 will be decayed. So number of undecayed nuclei will be how much? N naught by
1 by 4.
Exactly. And you know there is a formula, number of undecayed nuclei after time t, and that is nothing but n naught e to the power minus lambda t. Okay. So number of undecayed nuclei after time t will be n naught e to the power minus lambda t. So if there is a decay of 3/4, so number of undecayed will be how much? That will be n naught by 4, right? And n naught will be cancelled. Now if you take natural log, what will happen? You will have ln 4, that will be equals to lambda into t, right? It means the time required for 3/4 of part of the decaying, or time required to decay 3/4 of the sample, that will be 1 by lambda into ln4 or ln4 by lambda. And lambda is given, lambda we have calculated, right? So lambda is 1 by 324. So 1 by lambda will be 324 into ln4. And that unit will be what here? Unit क्या हो जाएगी? क्या unit हो जाएगी यहाँ पे?
ER.
Exactly. So it will be ER. Okay. So calculate this value. Basically, you will get 449.15 ER. So the time that is required for 3/4 part of the sample to be decayed. Next problem. The initial activity of radioactive sample is A0. The initial activity of radioactive sample is A0. The activity of the sample after 280 and 420 days. The activity of the sample after 280 and 420 days become
After how many days?
280 and 420 days become 6,000 becomes 6,000 and 3,000 becquerel respectively. है ना? So 280 days बाद शुरू से 280 days बाद कितना हो गया? 6,000 becquerel हुआ. And शुरू से 420 days बाद कितना हुआ है? 3,000 becquerel. So find the initial activity. So you have a sample initially A0 activity. So after 280 days, it becomes 6,000 becquerel, and after 420 days, it becomes 3,000 becquerel. है ना? ऐसा नहीं है कि 280 days के बाद 420, ऐसा नहीं. शुरू से 280 days बाद इतनी हुई है ना? And after 420 days becomes this much. तो शुरू से 280 days बाद this, शुरू से 420 days बाद this. So I have to calculate initial activity. Can you please try this one? Can you please try this one? Well, so will be, so as you know that activity of a sample, if you remember yesterday we was discussing, activity of a sample after time t becomes A0 e the power minus lambda t. Now this equation further I can write like you have a AT by A0, and that will be exponential minus lambda t. Now, if you take natural log both sides, you will have ln. You'll have ln AT divided by A0, and that will be minus lambda t. Now, if I multiply both sides by both sides by minus 1, it will be like that. And this minus you can bring as a power. That is the property of log. So you have a something की power inverse. इसका मतलब क्या हुआ है? So it will becomes A0 by AT, right? So basically I can write lambda t, that will be natural log A0 by A of t. means that lambda will become 1 by t and ln at by a naught.
A
Aji?
naught by 80, sir.
So A naught by
Yes. Thank you. It will be a naught by 80. So it's given after 280 days, this become how much? 6,000, right? So just I'll substitute the time. So you have a lambda that is constant for a given sample. So if you substitute that time, like if you substitute that t equals to 280 days, then 80 will become 6,000. And suppose this is your equation number 1. Means you substitute the time equals to 420, then your 80 will become how much? That is given 3,000. And let us take this is your equation number 2. So for any given sample, the decay constant is constant, right? So it is independent on time for a given sample. So after 20 days it will be same. After 420 days it will be same. So now I can compare these two equations. So I can basically write you have a 1 by 280 into natural log a naught by 6,000, right? And that will be equals to 1 by 420, and you'll have ln a naught by 3,000. And I can bring that 420 this side. Okay, so this 0 will be cancelled. And if I cancel with 14, so you'll have 3, and here you'll have 2. Right? So basically at the end, you'll have 3 ln a naught by 6,000, and that will be equals to 2 times ln a naught by 3,000. And the property of log I'll apply. I can bring this like a power, and this also I can bring like a power. Right? As you know, if you have a like ln a equals to ln b, it means a equals to b. You know this, right? So just I can write from here that a naught by 6,000 the power cube, that will be equals to a naught by 3,000 square. It means you'll have a naught chi square on the right hand side, and on the left hand side you have a naught ki power cube. So that power will be cancelled, and you'll have like this kind of scenario. A naught will have this kind of scenario. Check. A naught by 6,000 the power cube, that will be equals to 1 by 3,000 the power square. Right? So it means you will have basically that initial activity that is asked, and that will basically get 6,000 cube divided by 3,000 square.
240 answer.
Haji?
240.
240 or 2400?
2400. No sir, I'm getting 240. Let me check.
Check karo jara.
24,000.
24,000 or
Yes, sir. 24.
24,000.
exactly. Very good. It will be
Yes sir, 24,000.
Very good. Well, so then you have a next problem. Likho. There is 3.24 into 10 to the power minus 5%. There is 3.24 into 10 to the power minus 5% potassium chalice present in a human body. There is 3.24 into 10 to the power minus 5% potassium, mass number 40, present in a human body. The full stop. The mass of human body is 70 kg. The mass of human body is 70 kg. The mass of human body is 70 kg.
सर वैल्यू बताना 3.5 into
3.5.
सर क्या वैल्यू बताई आपने?
हाँ, ये तो लिखा है ना.
ओके सर.
There is 3.24 into 10 to the power minus 5% potassium is present in a human body, and if the mass of human body is 70 kg, then calculate the initial activity of potassium chalice. Calculate the initial activity of potassium chalice, okay, for potassium 40, and inside bracket it is given the half-life of potassium is given, and that I'll write here. That is 3.94 into 10 to the power 6 second. 3.94 into 10 to the power 6 second. 3.94 into 10 to the power 6 second. Understood that problem? So there is this percent potassium exists in a human body. The mass of the body is given. Human body 70 kg. Half-life is given. You have to calculate initial activity. Okay. कर लोगे? So half-life from here, you know that initial activity, we have discussed this thing, right? So initial activity means what? That is your A naught, and that is nothing but N naught lambda. So first of all, you have to calculate that number of potassium 40 present in a human body. That you have to calculate. Okay. So that percentage is given. You have a total number of potassium present inside human body that you have to calculate. So percentage from here I can calculate that you have a human body weight कितना है 70 kg, right? And 3.24 into 10 to the power minus 5% of 70 kg कितना हो जाएगी, है ना? Because you have mass of human body is this much, but only this percent of potassium is exist. So total total weight of potassium 40 is how much? मतलब कितना kg और ग्राम potassium human body के अंदर है? That I can calculate because total mass is this much and this percentage is present. So total weight or total how much gram potassium present inside human body, that I can calculate. That will be how much? कितना हो जाएगी? Tell me. 3.24 into 10 to the power minus 5 into 70. Suppose I'm writing gram. So from kg you have to write 10 to the power 3. That will be gram, right? And percentage given, so you have to divide by 100. So that will be that much gram of
22.75 into 10 raised to minus 6.
कितना आ रहा है?
22.75 into 10 raised to minus 6. I have found out in kg.
Oh, yeah, if you calculate in gram, then it will be like 2.26 into 10 to the power minus 2 gram. Can you check anyone?
Yes, sir.
Yes, sir. Same.
Okay. So this will be this much amount of potassium is actually present in a human body. But to calculate this activity, you have to calculate number of nuclei present. And the mass number is given. Potassium mass number was how much? 40. So now if I apply that molar concept, so 40 mass number कितना था आपका K40, right? So 40 gram potassium will have 6.023 into 10 to the power 23 nuclei. That's the concept of Avogadro number, right? That's the concept of Avogadro number, that mass number corresponding gram will have Avogadro number of nuclei. It means 1 gram will have how many nuclei? That will be 6.023 into 10 to the power 23 and divide by 40. Okay, so 2.26 into 10 to the power minus 2 gram will contain how many nuclei? That will be 6.023 into 10 to the power plus 23, and then we'll have 2.26 into 10 to the power minus 2, right? Divided by 40, and that is your actually N naught. The number of nuclei corresponding to this much gram will be the value of N naught. Is this clear?
Yes, sir.
Okay, so if you calculate this value, you'll get N naught, that will be 3.4 into 10 to the power 20 nuclei. Okay. So you obtain that value of N naught. Then you have to calculate that lambda. But we can do that because half-life is given. So 0.693
3 by
T half. T half was how much?
3.9.
3.94 into 10 to the power 6, right? So can you calculate this number? So if you calculate, you will get 0.17 into 10 to the power 0.17 into 10 to the power minus 6 second inverse. 0.17 into 10 to the power minus 6 second inverse. Okay. So now I can calculate that activity. A naught, that will be N naught 3.4 into 10 to the power 20, right? And then we'll have 0.17 into 10 to the power minus 6. Okay. So you calculate this, you'll get 5.9 into कितना आ रही है?
वो दिख नहीं रहा सर.
हाँ जी, नहीं दिख रहा है?
No sir, that is not up जा रहा है.
Okay. So I can write that A naught.
0.578 into 10 raised to.
A naught is N naught. N naught is how much? 3.4 into 10 to the power 20, right? And then we'll have lambda, and that we have calculated 0.17 into 10 to the power minus 6. And that unit will be how much? What? It will be decay. Decay per second, right? Decay per second. So calculate this, kitna aa raha hai? How much you are getting, anyone? Tell me.
5.78.
5
10
point
to 30.
5.7
Yes, sir.
5.7.
into 10 to the power 13.
30. Yes, sir.
And that will be decay per second means what?
Becquerel.
Exactly. Will be exactly. Okay. Now, if I ask you how much will be in Curie, how much will be in Curie?
2.6 into 10 raised to 6 में divide करना
तो
पड़ेगा.
that relation क्या था? 1 Curie किसके बराबर थे? 3.7 into 10 to the power कितना है? 10 to the power 10, right? 10 to the power 10 becquerel. तो एक becquerel किसके बराबर हो जाएगी? So I can convert this, right? So 5.7 into 10 to the power 13 divided by 3.7 into 10 to the power 10, and that unit will be in Curie. Okay. Calculate it. If you calculate that, then you'll basically get
1.56.
1.56.
Yes. Into 10 raised to 3.
1.5 into 10 to the power 3 QD. Okay. So this will be the, some problems. So tomorrow I'll do a few more problems. Then we'll proceed. Okay. So let's stop here.
Thank you, sir.